So let's say we've got a mass, and it's here on the ground. I just want to see it had a weight of 4 kilograms. So this is a 4 kilogram mass. And let's say, for argument's sake, its initial velocity is 0. We now apply an external force equals to twice the magnitude of the weight of this object. So if we draw a free body diagram for this, so at every point we have a force downwards, m times g, and we've got an upwards force 2 times mg. Right, so the upwards force is larger than the lower force, so the resultant force in this case will be just mg upwards. Right, so we're not only cancelling out the effect of gravity, we're actually applying a greater force, so the mass is accelerating upwards. And let's say this mass ends up, we want to figure out, let's say at some later time, this mass is 10 meters above the surface. And we still have our external force on it. We still have the weight going downwards. So we want to see what has happened. So first of all, we know that the initial potential energy, because this thing is on the ground, is going to be 0. Also, the initial kinetic energy is equals to 0 because it doesn't have a velocity. The final potential energy is equals to, it's now 10 meters above the surface of the Earth. The mass is 4 kilograms times 9.8 meters per second squared times 10 meters, and we found this was 392 joules. But its kinetic energy is not going to be 0. Its kinetic energy at this point is 1/2 times the mass times the final velocity squared. So we've got now both a change in potential energy and kinetic energy. So this force does a certain amount of work. Some of that work goes into just increasing the potential energy of the system. The other part of it goes into increasing the kinetic energy. So we also know the work done by the external force. In this case, the external force remains constant. So it's the external force dot with our displacement. So the external force is 2 times, because we say it's twice as large as the weight, so it's 2 times m times g times 10 meters. Both of these are upwards. And we find this is then equals to 700, let me just get that number, 784. It's late in the evening. So this is the amount of work done by the external force. Now, out of all this work being done, we can consider this energy being transferred into the system. So we know that 392 joules goes into increasing. Yes. Sorry. So 392 joules of this amount of work being done goes into increasing the potential energy. This leaves us with 392 joules that has to go into, remember this is like accounting, go to increasing the kinetic energy. So we must have, if we have conservation of energy, so the work done, which is equivalent to the energy transferred by the external force. So we're pumping so much energy into the system, that energy can go into one of two things. It can either go to potential energy, it can either go to kinetic energy, or both. So it is that total amount of work done is equals to, by the external force, is equals to the change in potential energy of the system. So some of this work increases the potential energy, and some of this work increases the kinetic energy. So we've got that if this is equals to 784 joules, if that is equals to, because remember we had nothing to start out with, at 10 meters displacement we had 392 joules of potential energy, so that's 392 joules. This means our kinetic energy change is also 392 joules. Our change in kinetic energy is equals to what we end up with minus what we started out with. This is equals to a half mv final squared. So we know that 392 joules is equals to a half mv squared. If you substitute in the values, you get that the final velocity is equals to 14 meters per second. So if you just make the velocity the subject of this equation, substitute in all the values, you get this. Now, can I check that these assumptions that I've made, if they are correct? So is there some other way in which you can see, well, would we get this final velocity out? And there is. We've got our equations of motion. Because we know that our force upwards is constant, so our resultant force is constant upwards. So we said our resultant force is equals to m times g upwards. So we've got the resultant acceleration, which is just the resultant force divided by the mass, which is equals to g, but now it's upwards. So the sum effect of this big external force and weight is to produce an upwards force, which gives us upwards acceleration. Because the resultant force is twice as large as weight, it just means we get now 9.8 meters per second upwards, instead of the usual downwards that you know from free fall. So in this case, it's up because of our external force. It's not only moving under the effect of gravity. And we know this is constant. So we know our displacement is equals to 10 meters upwards. So we can use this equation of motion, v final squared is equals to v initial, which is 0, plus 2 times the acceleration, which is 9.8 meters per second squared upwards, times our displacement. And if you put in the numbers, you find that the final velocity is indeed 14 meters per second. So we've got two completely different theories telling us exactly the same answer. That if you've got an external force doing work, that amount of work can go into potential energy or kinetic energy. If the velocity does not change, it all goes into potential energy. If the velocity changes, some of it goes into potential energy, some of it goes into kinetic energy. Right, and you can